Hello and welcome to Rock Engineering Practice Part 2, Rock Slope Engineering. In this session, we will learn how to analyze rock slope stability using modified rock mass rating for slope, or IMR slope for short. Apart from stability assessment, IMR slope can also provide support design guide for rock slopes. As we have learned earlier in rock mechanics, rock slope stability is a function of rock mass quality. Good quality rock mass will give a more stable rock slope or require less rock support. Therefore, rock mass quality classification can be a basis to assess rock slope stability and the slope support requirement. IMR is a rock mass quality classification system, and it provides quality rating for the rock mass. Generally, a high IMR means good quality of rock mass, and the slope is more likely to be stable and requires less support. IMR is used widely for underground excavation and support design, and it can also be used for slope stability assessment and slope support design. The basic IMR presents the rock mass quality on site without considering the nature of the project. For slope excavation, engineering has a high impact on the changing of rock mass quality, particularly influenced by the geometrical relationship between the slope and the joint sets. Therefore, to use IMR for slope, adjustment for joint orientation must be applied with respect to the slope orientation. Why is joint orientation so important in slope stability? Let's take a look at the illustration on this slide. Imagine here is a north to south running road. The road cuts the rock mass to form two slopes, one on the left and the other on the right side of the road. The rock masses on both sides of the slope is the same rock mass on site. Yet, let us assess the stability of the left and the right slopes. Do you think they are equally stable? No, you will see they are not equally stable. The left side slope is more likely to fail, as you can easily visualize that sliding down of the blocks. The right side slope seems quite safe. Well, the same rock mass, because it is cut a different direction, the slopes have very different stability level. In other words, the quality of rock mass on each slope now are very different. The rock mass of left slope is poor and unsafe, while the rock mass on the right slope is good and safe. The difference is created by the introduction of slope orientation in relation with the joint orientation. Rock mass quality for a specific project can be altered by engineering. For example, how the slope is excavated. We have learned how to compute the IMR, the rock mass rating, in rock mechanics principle class. Here, I reproduce the IMR table. IMR is assessed based on 5 rock mechanics parameters: the strength of intact rock material, the RQD, the joint spacing, the condition of joint, and the presence of groundwater. By assessing each rock parameter, we can obtain the IMR value. You may wish to revisit section 4.3 of rock mechanics principle course to recall how to use the rating to get the IMR for those rock mass parameters. With those ratings of 5 parameters, we can get the basic IMR value by summing them up as shown by the up table. With the basic IMR, we can classify the quality of the rock mass. This is the quality of the rock mass in situ, without considering the engineering activities. The table below provides suggested rating adjustment for joint orientations. The adjustment is based on the geometrical condition of joint being favorable or unfavorable for construction. For slopes, there is no adjustment needed for a very favorable joint orientation. For favorable condition, adjustment is -5. For fair, -25. For unfavorable, -50. And for very unfavorable joint condition with orientations, the adjustment is as high as -60. Note the maximum basic IMR rating is 100. Therefore, adjustment rating of -60 is very significant. It can change the rock mass quality from very good to poor after such adjustment. However, the original IMR method did not provide methodology to obtain adjustment systematically. Later, Professor Manuel Romano in Spain developed a systematic and quantitative approach to obtain the adjustment for rock slopes. The adjustments are accounting for several factors influencing rock slope stability. Joint orientations in relation to the slope orientation are the main contributing factors in the adjustment. Slope failure by plane and wedge sliding, as well as toppling failure, are considered, as we will see below. The adjust IMR system for slope is also called slope mass rating. Here, to be consistent with IMR, I use the term IMR slope just to classify this system is linked to IMR. The adjustment has 4 parts, namely F1, F2, F3, and F4. F1, F2, and F3 are orientation-related adjustments, and F4 is adjustment for slope excavation quality. The total adjustment is equal to F1 times F2 times F3, then plus F4, as expressed by the equation on this slide. For rock mass quality rating for slope, the basic IMR plus the adjustment as shown by the equation, IMR slope equals to the basic IMR plus F1 times F2 times F3, and then plus F4. On the next slide, we will learn how to obtain F1, F2, F3, and F4. Adjustment of F1, F2, F3, and F4 can be obtained from this table developed by Professor Humana. Rho A is to calculate the angle between joint dip direction and the slope dip direction. The smaller the angle between the dip directions of the two planes, the more parallel are the two planes. Since being parallel gives more potential of plane sliding, and this becomes unfavorable, it leads to the higher F1 value. Rho B is a joint dip angle. We know that the higher or steep dip angle means it is easier to slide down, particularly when the dip angle is higher than the frictional angle of the joint plane. Typically, joints have a frictional angle around 30 to 40 degrees. And this is why when the dip angle is higher than 45 degrees, the possibility of sliding is higher as 1, as reflected by F2. Rho 3 is to calculate the joint dip angle minus slope dip angle. If joint dip angle is smaller than the slope dip angle, then we know the joint is daylighting on slope. Therefore, negative C value means joints are daylighting on the slope. As discussed before, daylighting is the single most significant condition of sliding failure for both plane and wedge sliding failures. F3 is the fact assigned to represent daylighting characteristics and has the maximum value of minus 60 when the joints are definitely daylighting on the slope plane. Now if we have any joint plane near parallel to slope with a steep dip angle that is higher than the friction angle, and the joint plane is daylighting on the slope, then we are certain that we will have sliding failure. The adjustment from F1, F2, and F3 is 1 times 1 times minus 60, and is minus 60. The maximum adjustment we can get from orientation adjustment. F4 is reflecting the condition of slope, particularly to account for badly excavated slope surface. For example, bad blasting practice. Here, standard blasting is considered as normal and has no adjustment. Positive adjustment is given to high quality blasting practice, while negative adjustment is given to bad blasting practice. Good blasting practice such as precipitating and smooth blasting will generating low damage of the rock mass forming the slope, and hence the slope has low failure potential. Natural slope has the highest positive F4 adjustment since the slope condition has been stabilized for years. Let us recapture and summarize what adjustments F1, F2, and F3 representing in the table we just gone through. Parameter A checks if the joint is parallel to the slope by comparing joint direction to slope direction. If A is approaching to 0, it means high parallelism of the two planes and a high potential of plane failure. It is also possible to estimate F1 using the equation f1 equal to 1 minus sine A and the square. Parameter B checks if joint is steep enough to slide. Sliding potential increases with higher joint tip angle. Apart from getting F2 from the table, F2 can also be estimated by F2 equal to tangent B and square. It should also be noted that consideration of toppling failure is included in the steep joint dip angle greater than 45 degrees, with F2 equal to 1. Parameter C checks if joint is daylighting on slope. By comparing joint dip angle and the slope dip angle, a negative C value means joints daylights on the slope, and also means the greatest potential of sliding failure, and therefore leads to highest F3 value. After adjustment, each IMR slope represents the rock mass quality of each slope being assessed. The objective to obtain IMR slope is to provide assessment of slope stability and to provide design guidelines of slope support. The table here shows how the IMR slope values in column 1 gives the slope rock mass quality class in column 2. Slope stability on column 3 can be estimated based on the slope IMR. If slope is unstable, possible failure mode, as in column 4, can be associated with the IMR slope rating. Rock slope support design, as shown in column 5, can be recommended, again based on the IMR slope. As seen from the table, if IMR slope value is higher than 81, it indicates that the rock mass of the slope is of very good quality. The slope will be completely stable, no failure is expected, and no support is required. If IMR slope is between 61 and 80, the rock mass of the slope is of good quality. The slope will be stable in general. There are possibilities of some block falling, and spot bolting may be required. If IMR slope is between 41 and 60, the rock mass of the slope is of fair quality. The slope will be partially stable. Slope fails along some joints. Blocks and wedges will slide, and the systematic bolting will be required. If IMR slope is between 21 and 40, the rock mass quality of the slope is of poor quality. The slope will be unstable, circular failure, planar, or large wedge failure may occur. And the important support and the corrective measure are needed to be considered for this slope. When IMR slope is below 20, it means that the rock mass of the slope is of very, very poor condition. The slope will be completely unstable. Slope will fail by large planes, wedges, or circular failure. And apart from using very heavy support, re-excavation of the slope, for example, changing to a gentler slope angle, should be considered. I'm using an example here to reinforce the learning on using IMR slope. The problem is an old problem we saw at the beginning of this session. the north to south running road is to cut a rock hill. It will create two slopes. The left side slope is facing to the east, and the right side slope facing west. The hill has the same rock mass, and the basic IMR of the rock mass at the site is 86. The design slope angle is to be 70 degrees. The rock mass with basic IMR 86 is of very good quality. Competent, strong rocks and containing two main joint sets with orientations of 087/56 and 195/10. The slope is to be excavated by normal blasting. You, as a rock engineer, are asked to review this design. Specifically, asked to assess the stability of the slopes using IMR slope. How are you going to do it? Well, we will analyze the slope stability using IMR slope following the steps. First, for each slope, find adjustments F1, F2, F3, and F4 against each joint set. And then compute IMR slope for each slope. Finally, we can assess slope stability and the slope support based on IMR slope. Let us start with the left side east-facing slope. Being east-facing, the dip direction is 090. The dip angle of the slope angle is 70. We can compute the adjustment using the table on slide 7 against both joint sets on column 2 and column 3. The results are shown here. For the first joint set, which is 087 and 56, A is on the direction, and it is 87 minus 90, which gives the absolute value of 3. F1 therefore is equal to 1. Joint dip angle is 56 in row B. Therefore, F2 is 1. Row C deals with joint dip angle minus slope dip angle. That is 56 minus 70 gives minus 14. From the adjustment table in slide 7, we get minus 60. F4 is 0 because it is normal blasting. The total adjustment is F1 times F2 times F3 and plus F4. It gives minus 60. The adjusted IMR for the east-facing slope is now 26. We can do the same computation for the second joint set with orientation 195 and 10. As shown in the table, the total adjustment for this joint set is 1.35. The adjusted IMR slope is 85. Combining the adjustments for both joints set, the worst is from the first joint set. the east-facing slope is having a poor rock mass quality with IMR slope rating of 26 because of the influencing from the first joint set on the slope. With the IMR slope and the slope stability table on slide 9, we can assess rock mass quality stability, failure mode, and support requirement. With IMR slope equal to 26, the rock mass on the slope is of poor quality. The slope is unstable. Sliding is the main failure mode due to daylighting of the first joint sets. Support requirement suggests is important support and possibly corrective measures. Similarly, we can work on the adjustment of two joint sets on the west-facing slope, whose orientation is 270/70. Following the same steps, we will get adjustment of -9 and -1.35 for the two joint sets on the west side facing slope. IMR slope we get for this west facing slope then become 77. It is 86 minus 9, which representing good rock mass quality. The slope is generally stable with some possible minor toppling. Support recommendation is spot bolting. Let us go back to the east facing slope. We have a problem with its stability. It is unstable and requires substantial support or correction in design. Can we improve the rock design by making the slope more stable, requiring less support, and reducing the construction cost? We notice that the main contributing factor is the daylighting of the first joint set, with dip angle 56 degrees. Imagine if we cut the slope with slope angle equal or slightly smaller than 56 degrees, which is joint dip angle. Then we eliminate the daylighting and eliminate the sliding potential. The table on the left is to reassess the east-facing slope with reduced slope angle to 55 degrees. What do we get from the analysis? IMR slope now is 80 to 86. The slope is stable and we do not need support. What a difference from the initial design. As also illustrated by the diagram on the lower right, with slope angle at 55 or 55 or 56 degrees, the east-facing slope does not have sliding problems. In fact, we can optimize the slopes by cutting the left slope to 56 degrees and the right slope to a steeper angle, say 80 degrees. IMR slope is a powerful method. Through quantitative rock mass rating for slope, it provides a practical mean for slope stability assessment and a support design. It should be noted that the IMR slope system used for slope stability assessment and support design guide does not consider slope height. Therefore, for very high slope, such as those in surface mines and quarries, additional assessment is needed to examine the stability of the overall mine and the quarry slopes. The IMR slope system does not consider external loading such as machines and buildings on the top of the slope. If the slope is subject to such loading, then the loading condition must be considered in stability assessment. Similarly, if the slope is close to blast or is subject to potential earthquakes, then the effects of blast and earthquake loading should also be considered. Right, we're coming to the end of this session. I hope you are now able to use IMR slope to analyze slope stability and to design the slope including support. Enjoy learning and see you at the next session. Bye.